you want to introduce Travis, next one?
So now I have the pleasure to introduce the team from the University of California, Santa Barbara, which is represented by Travis Bashir. So yeah, Travis, the floor is yours.
Hello. So I am here presenting on our work for directed energy propulsion of small wafer sats. We work in the UCSB Deep Space group for experimental cosmology. We're funded through a NASA Innovative Advanced Concepts that we just got recently. And also on Skype is my advisor, Philip Lubin. So, Phil, do you want to say hi? I think you can say hi.
Hi.
Wait, I think he's on. Wait, say, yeah, oh, yes, greetings, he says. So yes, here is our team. I had the pleasure of leading an undergraduate team at our UCSB, and that included Alex Lang, Kyle McDonough, Sebastian, and Kyle. And here's our, this is Phil, you can't see. I'm Travis. And so, I just want to start off with looking at where we are now and what we have for our path to the stars. We really need to start rethinking our long-standing approach to the stars of using chemical acceleration, because these are highly non-relativistic cases. As shown with this plot, I think you can see this laser, but you have, this is a mass versus beta, so we can see that chemical acceleration is not going to get us our relativistic cases that can get us to stars in a shorter time period than what we have right now with chemical acceleration.
Pointer.
Yeah, thank you for a pointer. That would be perfect. And so what we hope to do is directly couple light to macroscopic objects. That's where the electromagnetic acceleration comes in. And so I really want to take it back to what is the point of all of this. I feel humans are explorers. We all start down this quest in life to learn things, and one thing that is just so massive that we have not even started to explore yet is the interstellar medium. And there are so many different things that we can see while we go through the interstellar medium. We have a solar gravity lens, we have the Oort cloud, we have our helipods, we have the interstellar winds that we can analyze, and of course we have Alpha Centauri, our next closest star system. So how do we get to the closest star, Alpha Centauri? We need to start with our photon drivers. So for the past 3 years at UCSB, we have been analyzing and looking at a D-star system, which is a multi-simultaneous target phased array of lasers, and which is powered by solar PV. These are photovoltaics. And so what we hope to do is get a space-based laser that we have. We actually have a paper coming out on where we would put this space-based laser to propel our spacecraft to these distances that we're talking about. And that's coming out this year. Zhang et al. 2015 in SPIE. You can find it on our website later on. And so how we classify these D-star systems is 10 to the 0 would be a 1 meter system, and so on and so forth. And so D-star 4, which is what we're looking at for Alpha Centauri, would be a 70 to 100 gigawatt laser. And so what this laser is a phased array laser. And what it does is we take one single seed laser and have many small lasers amplified by one of our amplifiers. We have a picture of it right here. Amplified, so we get an optical array of all these lasers. And what happens is with the phasing, what the phased array laser gives us is a mechanism for beam formation and beam steering. And so just to outline our most extreme case is a 1 gram spacecraft and a 1 gram reflector. This will reach Alpha Centauri in 15 years with a D-Star 4 system. It will achieve up to 25% C. And this is with a 1 micron thick reflector. We're not talking, this is like technology we have now for reflectors, not what we could get with more futuristic technology. And just again to tell you that this is a 10 kilometer by 10 kilometer array of lasers. So here's an artistic rendition of our system. And so the spacecraft speed is defined by this equation here. And what it shows is that the scaling of speed is a mild function of payload mass, which is m to the negative 1/4. And this is a non-relativistic case. And so what this means is that as you decrease your payload mass and your thickness of your reflector, you're going to get more speed. And this current reflectors have thicknesses in the 1 to 10 micron range, and we can see in this plot we have for different micron thicknesses of different, so we have 100 gigawatt and 7 gigawatt, we can show the speeds that we can achieve at certain payload masses. So I just get this some water in a second. So for our laser sail reflectors, for our non-wafer case, which is our 1 gram spacecraft, we could use multi-layer dielectrics on metallized plastic or glass films. This helps get up to about 5 nines of reflectivity. And these would be tuned to our specific wavelength of our laser. And so we just have a plot showing that. But for our wafer case, there's so much flux on the reflector that if we used a metallized plastic or glass film, it would actually start to heat up and vaporize our sail, which we don't want. So what we'd have instead is a multi-dielectric on glass with no metal. And this is similar to what you have in like a fiber optic cable. They use glass actually inside fiber optic cables that can get up to much more power than 100 gigawatts. So just to kind of show the wide array of our mission and beyond the scope of a 1 gram spacecraft is once we build our system, our D-Star 4 100 gigawatt laser, we could send out an array of spacecrafts. And just for, let's say for our 1 gram spacecraft, it actually takes 10 minutes to reach about 16% the speed of light, and then with continued illumination, you get up to that 25% mark very quickly. So this would be very short acceleration periods. So at 10 minutes to excel 1 wafer, you could map 40,000 per year on 1 per square degree of the sky. And this would be a total mass of all the wafers of 80 kilograms. And so for another case is for 100 to 100,000 kilogram payloads, we could start using those for interplanetary missions at much slower rates, which would be a few days to weeks. And so yeah, just to kind of point out, this technology is more on we like to call it the real axis rather than the imaginary axis, whereas fusion rockets and that futuristic technology kind of lies on that imaginary axis, and we're proposing a realistic approach to spacecraft travel and interstellar travel. So here again is just kind of showing, we have an artistic rendition of our wafer scale spacecraft. You can see our wafer on board here, and just an artist version of a 100 kilogram craft similar to Voyager that would reach 1.5% C, which is nearly 300 times faster than Voyager. And that's an incredible feat to have, and just shows that from 1 gram up to 100 kilograms, we can send a wide variety of spacecrafts. And again, I just want to show that we can actually send up to a 1 kilogram spare craft mass, which would have a 27-meter reflector on it, to Alpha Centauri within our 100-year Project Dragonfly requirement. And we also meet that extra bonus for our 1-gram spacecraft and our 10-gram spacecraft of getting 10 light years away. So that's actually pretty interesting to look at. And so our wafer-scale spacecraft combines nanophotonics, MEMS, and electronics with recent works at UCSB on SI nanowire thermal converters to design a wafer that also has an embedded RTG to power the many decades over space. And I'll go into this a little more in the presentation. We also would have small embedded photon thrusters to rotate our spacecraft if we needed to. And so this is just our 100 gigawatt case, a 1-gram wafer set, outlining all the different types of photon rate, spot size, acceleration. You can kind of take what you want from this graph. And so to kind of point out the technology that we're talking about is the wafer technology and how it's advancing so quickly. We started out in the 1990s on the process level, and then in 2000 we got MEMS level technology, and now we're in this phase of packaging level, and soon we'll be on of integrating MEMS into wafers, and this is coming up in the next 10 years. And this is what we're talking about doing for many of our scientific data instruments. So this is a very near-term situation. And so how we would communicate back with Earth is with small photonic phase array lasers with a silicon-on insulator. And so this is actually a work in our electrical engineering department at UCSB. And they are looking at using actually integrated phase array lasers on board to communicate back. And what this allows is free space beam steering of where we would point this, and it also allows no moving parts for our communication system, which would be much less susceptible to mechanical wear. And so for our onboard power would be using our silicon nanowires for thermoelectric conversion. So we could actually, here's a picture of a silicon nanowire composite. We'd have our SI substrate contact and then our top contact, and you'd have your silicon nanowires that would help keep that temperature difference of 56 Kelvin. And this actually would only be 650 nanometers by 650 nanometers on our spacecraft, and would fit very easily on our spacecraft, our 1-gram craft. And so I just wanted to point out our photon thrusters of LEDs. So at 3.3 nanonewtons per watt, this has been analyzed very much to get that. That's just, you would have an LED shine off the ends of our wafer to rotate it, and we can actually rotate it 90 degrees in about 50 minutes. This would help for orienting the craft to get a picture of Alpha Centauri maybe when we get there, or doing something like that. And just for onboard power and RTG, there's a lot of history that goes into RTGs, and we've actually looked at a very interesting one was one that they put in pacemakers back in the 1970s and generated 0.3 milliwatts by this company and by Numet Corporation. And that's actually pretty interesting that they were able to scale it down so far. And so what we propose doing is using about 0.275 grams of plutonium, Pu-238, which would help generate 5 milliwatts of power to produce about a 370 bit per second data burst within a 1 watt burst. So what we would do is we would store some power in a capacitor, and then we would be able to have a 1 watt burst, which would provide us a 370 bit per second data burst. And just to point out, we assume a 6.5% thermal to electric conversion efficiency. And so here's just a chart showing our power and communication for each spacecraft that actually would be able to reach Alpha Centauri. And we actually look at, in this plot, you can see we use the reflector for the communication rather than before we assumed for our 370 bit per second, we assumed using 10 centimeter by 10 centimeter wafer that we have, like the back of it as the communication. And so yeah, this one is using the reflector, and we get much bigger data rates back to our laser system back here on Earth, or orbiting around Earth. And so, moving on to our mission design, we propose using the shotgun approach. So what that is we send out many small scale wafers, in that because there's a lot of relativistic dust and there's many things that could happen to each wafer, we want to amortize that cost over a wide variety of missions. So we could send out, like I said, 40,000 per year. This would be an incredible feat because each one only takes 15 years to get to Alpha Centauri. We can make changes to our system, and we could also put different electronics on board to take different measurements. We can have, we could also send a 1 kilogram craft with 500 smaller wafer scale crafts to analyze Alpha Centauri. But one thing I would like to point out is that we do not decelerate to an orbital to be able to orbit Alpha Centauri. We actually just pass Alpha Centauri and take data as we pass by. Because if you're going 25% the speed of light, it's very hard to slow down. So the wafer class should. So what we did is we looked at the distance from the Sun to Pluto, which is roughly 100 AU, and we kind of took this as a data-taking range for Alpha Centauri, and that would have about 55.2 hours, amounting to 993 bursts of data. That's at 370 bits per second. This is actually very interesting because we would be able to take pictures and send back, and some other scientific objects. So we also look at using a mag cell for our bigger class spacecrafts, but that technology is very futuristic and doesn't seem feasible at this point. So there are many challenges to overcome in getting to the stars and using our wafer scale spacecraft to do that. One of which is stability. If you think about, let's say you take my phone and you squirt a high power hose at it, right? You're going to get all sorts of chaotic things happening, and it's not going to just go straight. This is why we need to do some sort of stabilization, and so we need to use the choice of our structure, such as maybe like a bubble or spinning it, may help for stabilization, but we really need to look at this in the future. And also deceleration, if we would like to do that, is a big problem. And so one thing you have to think about as well for laser propulsion is the laser that passes through your reflector. Because if you have this 100 gigawatt laser passing through your reflector, you're going to, just as you would heat up the metal sail, which is why we can't use that, you would heat up whatever sits behind the sail. And for us, what sits behind the sail is our wafer. So what we would do in order to kind of cloak our wafer is put fiber optic cables around our wafer and direct the laser beam around the wafer. That way the laser is not hitting the reflector and heating it up and vaporizing it. We also have to take into consideration there are extreme g-forces at accelerating something to 25% the speed of light in roughly 10 minutes. So for the wafer, we actually looked at artillery rounds that the DoD has and what is used right now, and they actually can withstand similar Gs with their certain technology. So that that is the problem, but the reflector itself, we have to have some sort of support structure for that. So once you get a space-based laser up in space, there are a wide array of things we could do. We've looked at for 3 years also at using lasers to ablate asteroids and move them on a trajectory path for Earth. We also have considered the SETI uses of our laser to maybe beacon as a signal to other planetary systems and establish potential long-range communication. We also be able to observe the absorption lines of the asteroid, again, asteroid uses, and also mitigating space debris would be one option. So all these, for the cost of you asked about the cost of putting a space-based laser. The economic feasibility is, we looked at fitting it onto a Block 2, and it actually cost about $1 trillion, more like $1 trillion range. So obviously that is very long-term and very expensive. But what we hope to do is amortize that cost with all these different scientific objectives that we could use the laser for. And we could also we wouldn't have to send up this all at one time. We could do an array and put them together. And so coming back to where do we move along down this roadmap and where do we start? We start with CubeSats to raise awareness for interest and proof of concept, and we have conferences like this. And we also we actually in our group are looking at laboratory measurements and demonstration of directed energy propulsion. And so what I have shown here, this actually has an asteroid sample on it. I designed a torsion balance that hangs from a torsion fiber. And what we do is we have a 40-watt CW laser that goes through a fiber optic cable and then through a lens, and that goes through a window into a vacuum chamber to simulate space conditions. And so what happens is when you get the ablation process, you start ablating on this end, and our torsion fiber, our torsion balance rotates this way, and we measure those rotations with a secondary laser pointer shining off a mirror into a laser detector. And so to test to measure laser propulsion, we plan on putting some sort of reflector on the end of our torsion balance rather than an asteroid sample, and scaling down the thickness of our torsion fiber to get bigger rotation. And so here's just a roadmap to getting to where we want with a 10-kilometer array. And we are around step 1, step 2 right now of potentially getting a CubeSat up in space and testing that and doing some laboratory measurements. So this is a very long-term process, but we are trying to start on this long-term roadmap. So thank you, and we can open up for questions. And if you have any questions, you could email both me and my advisor, Luke, right there. And then there's our website with those papers that will be coming out in the next couple months.
Two questions. Very good presentation, thank you. So the first is, you talked about reflectors 1 to 10 micrometers in thickness, and you said that future technologies might be able to reduce that. Do you have a vision for that technological pathway?
We don't right now, because we've actually just been looking at the technology for right now in the next 5 years, which is those 1 micron thick reflectors. Using graphene is one potential possibility, but that's very down the road.
Okay.
Yeah.
Okay. So the other question was, you were talking about using 0.275 grams plutonium-238.
Yeah.
Producing about a 1 watt of power. So you've got...
it would produce 5 milliwatts.
5 milliwatts of power, okay. Right. So that means that you're producing 40,000 per degree of the sky. Mm-hmm. And that means there's, for 80 kilograms total mass each cycle, there's 290 1,000-ish. That gives you 7 essentially cycles of doing that. So in other words, after 7 iterations, you're going to run out of plutonium-238. So what's your other plans? What other RTG materials could you use?
Oh, so we actually have in our paper, we have some different different things rather than plutonium. They actually, in Cornell University in the U.S., has looked at using a radioactive, I think it's a nickel type of radioactive decay, and they use that they actually put that on one of their spacecrafts they sent up to space. So we looked at that. The problem with that, the thermal to electric conversion is a little less than what we're talking about. So that's one possibility, but we're looking at things like that.
What about americium-241?
Yeah, we looked at americium, but it's a little harder to get than plutonium, so that's why we found plutonium. But we in our paper
that's not hard to go with it.
Yeah.
Okay. Yeah. Thank you.
So you would start with the ground-based laser.
1 second. Yes, Phil.
I don't know if you can hear me.
They can.
Yeah.
Can you? Okay. So americium and other radioisotopes are possible. Americium is actually used in smoke detectors, as I'm sure you know, and it's relatively easy to acquire. But there are a number of radioisotopes that can be used. You know, the number of 40,000 per year of wafers is just to show you the magnitude of what could be done. Not that you would choose to have all of your missions be, gram level. But if you did choose to do that and wanted to shoot out 1 per square degree in the sky, it would take you approximately 1 year to do so. I don't think that would be the optimal way to, begin a program, but it's a possibility.
The question was, so you would start with a laser based on Earth, and then move it to the sky, but then it would be orbital, would be satellite based, and would be pushed away as we learned before, right? Or how would it be kept?
Phil, do you want to answer?
Yeah, okay. So, the ground-based testing is purely for test phase. These are directed energy systems, which are used for other programmatic purposes. And the reason we're going this route is because of involvement in other programs where this works very, very well. There's a number of scaling issues which at the moment are very favorable for this. It does not appear to have a limitation. So no, you would not start with a large phased array on the ground and then move it to orbit. That wouldn't be logical. It wouldn't make sense. But you do start on the ground with small test systems which are already being built, and then you evolve that to a high enough TRL to move it into an orbital configuration. But the way this thing is put together, every sub-element is relatively small. Each amplifier is about 1 kilowatt. Every sub-element optical system is roughly 1 meter, and so they nicely fit into a common launch vehicle, which you'd have to have a number of those launch vehicles. But everything is designed to be modular and scalable, so it's relatively compact. For individual elements, you just have a lot of them.
Okay, but the orbital array then needs to be stabilized somehow. How would this be done?
Are you asking a question of what happens to the photon pressure that pushes back on the array?
Exactly, yeah.
Okay, so if you have 100 gigawatts, that's 330 newtons pushing back on the array when you fire it. Of course, you have actually have more than that pushing on the array from sunlight that's illuminating it. So it's a balance between what's pushing back from photons going out and what's pushing on it from the sun. So what normally happens is one tries to balance those two because there's a combination of the two effects. I agree, you have to actually go ahead and stabilize a platform like that. Perhaps an ideal configuration would be not to put it in low Earth orbit, which is cheaper, which is why we're baselining that, but to put it into either translunar orbit or even on the moon itself is a possibility, although there's a fair amount of dust that you have to worry about on the moon. So I agree with you, although again you have to keep in mind that any spacecraft you put up is illuminated by the sun and radiates at the same time, so there's a thermodynamic balancing that goes on, and depending on which wins, you're going to, in the end, have some differential instability that you have to overcome. I don't think that's, in what we've looked at, that's not the major limitation of this. It's certainly something that has to be thought about, but it's not the major problem.
Okay, what about the degradation of the spacecraft? If you go to Alpha Centauri with 25% of the speed of light, what is your assumption about the degradation?
In terms of relativistic dust hitting it?
Yes, and interstellar hydrogen.
Yeah, so we looked at it a little bit, and we actually showed in our paper using we would send. They looked at like right before when you get to let's see, when you're kind of moving along after you've gone up to speed, you send out some particles in front of you, and those you'd send out some dust, like a dust cloud, and that would absorb a lot of impacts. And that's one way to do it. But the main way we're trying to do it is trying to send out a lot of spacecrafts, because if this does happen and one fails, then we have so many more to back this up.
I mean, sending out a lot of spacecraft doesn't really help unless you send out the spacecraft like in a row. I mean, then the interstellar dust would, or the hydrogen particles would eat up the first spacecraft, then the second, then the third, etc. But they will probably not remain like in this order once you have sent them out. So sending them out like in a cloud doesn't really help, because each of the spacecraft is degraded at the same rate. So how do you cope with that?
So if you look at the various constituents you'd worry about, a dust particle being hit by a relativistic craft is going to do a lot of damage to it, and they just completely take it out. If you look at the number of dust grains that you would encounter on a trip out of the solar system, some of which you can get by studying the zodiacal light distribution, for example. And then in interstellar space, you can study that based on the cosmic ray distribution. We know more or less what the dust distribution and the hydrogen distribution looks like. If you're hit by a significant dust grain, you're basically going to destroy a good fraction of your spacecraft. The probability of being hit by a dust grain on any given trip is not unity at all. Being hit by molecular or atomic level constituents does not destroy the spacecraft in general. It does tend to degrade it. You're going to have effectively just like a cosmic ray radiation field, but at fairly low energies. That is easier to handle. We would handle that by redundancy within spacecraft. So even if we took out part of the spacecraft, we would have multiple redundant independent elements. I agree with you. That's something that has to be studied. One of our part of our effort on the roadmap is to look at long-term radiation damage for various parts of the system and look at how we would overcome that with watchdog timers on various parts of the way for multiple redundant parts. It's definitely something to think about, but it's not a unity degradation. The probability of taking out spacecraft is not one along the line of sight out to the nearest star.
So I agree with you, but the hydrogen, so about the dust, the hydrogen density is about something like, I think it was like 1.01 hydrogen atom per cubic centimeter or something like that. You probably know better. But it's actually a constant stream, and once the hydrogen atom impacts a spacecraft at that speed, I think there's some, I don't know if there's gamma rays or, I don't know, X-rays generated by the impact or something like that. I think it's quite violent in a sense, but you probably know better about this aspect. But I guess the effects and phenomena are probably quite complex, and I'm a little bit skeptical whether it really works at these speeds, to send out the spacecraft at these speeds, and not to expect significant damage after a while.
So in Project Orion, as you know, they looked at using beryllium and other high Z materials as a mild shield. They used a thin layer of beryllium. So we looked at that. We looked at putting a thin layer of beryllium on our system and other tungsten, other materials to act as a shield going out. That increases the mass of the system. It doesn't completely prevent us from achieving relativistic speeds, say above 5% of the speed of light or so. But it's something that we'd like to look at before we would ever commit to doing that, because it does significantly increase the mass, which is not a particularly useful mass in terms of functionality. But it may be necessary. I'm not convinced yet. I looked at the numbers for hydrogen, and you're not coming with a relativistic. I mean, it's not a highly relativistic beam of hydrogen. It's a very mildly relativistic beam. So I'm not convinced yet. We've looked at the numbers. They look like maybe we don't need that, but definitely something to look at. Luckily, we could put our stuff in a beamline. Particularly for the smaller systems, you can literally put the entire spacecraft in a beamline and hit it with both particles, hydrogen and molecules also, as well as accelerated dust grains. So you can study actually some of the interactions in the laboratory before you ever go into space.
Can you remind me again what your communication system was? How are you getting the information back?
Yes, do you want to outline it?
Sure. So there's been interesting work at UCSB on integrated laser communication system on a chip. And so our baseline is a phased array laser comm on a chip. All the plots you see are based on a nominal phased array laser on the wafer with no additional optics, with the exception of we did allow the reflector to be used as an optional optical element. That increases the data rate of the Earth, but it is actually not necessary to get data back, just gives you a higher data rate. So the answer to your question is a integrated phased array laser communication on the wafer, which is essentially powered by the RTG, which runs continuously. The RTG runs continuously. The energy is stored on board, and we're looking at two methods. One is a sort of pseudo supercapacitor, and the other is an electrochemical system that we have to keep warm. So we're looking at that carefully. And then about once per 10 minutes or once per hour, we would burst a watt or a few watts of laser comm back to the Earth. And so the plots that Travis showed you come out of two papers, which will one is Impress in JBiz, which should be out I think in the next 2 months. It's been in the system for about 2 years from an ICRIS conference. And another one was submitted to JBiz in April, which is the roadmap to interstellar flight. All of those are on our website, which you can take a look at, and they form the basis for the reports and presentations that go through the mathematics and a lot of the particulars. For LaserComm, we ran the zodiacal background, we ran the cosmic infrared background, the CMB is basically irrelevant, the galactic emission is largely irrelevant, thermal emission from the structure is largely irrelevant. The two big ones are zodiacal light and the CIB, cosmic infrared background. And so we ran a link margin, which is what you see on the plots, and that forms the basis of computing the data rates back at the Earth. We assume, which is critical, that the reception is done by the same structure which transmits the beam to initially accelerate the spacecraft, i.e. the laser array is used in reverse as a reception system. If you look at the way we build our laser array, it can be run backwards to receive signals as well as transmit them. That is absolutely critical. Otherwise, you're not going to get significant data.
Has this been demonstrated in the lab, this technology, in anywhere?
Well, which part of the
this optical phase array communication? What TRL was this?
Okay, so there's a plot, I think, in slide 18, if it's the same as I have.
Yeah, I have it open, actually.
Okay, so those plots which show the 3D contour plots, those are actual laser communication on a chip, on a small part of a wafer. It's a silicon photonics based. Those are done at 1.55 microns. Whereas we would do it about the same, maybe a little bit shorter wavelength. But that's real data that you're seeing there.
Before it was just American.
Yeah, so it's that was published in 2014. It's relatively new, and that was done at UCSB. I'm not saying it's it's not a TRL 6 yet, but does not look like this is a showstopper to implementing it. But it's one of the things on our roadmap. But this one already exists, at least at the TRL 3 or maybe 4 level, so you can see the data itself.
What's the signal to noise ratio you used for your communications calculations?
Sure. So we assume anywhere from 1 to 40 photons per bit. What's been achieved in LaserComm is less than 1 photon per bit already, but in the plot that Travis showed you, that assumes 10 photons per bit, which is fairly conservative. And the signal to noise is based on 2 things. One is the signal, how many photons do you emit, and how many of those get back to you through beam formation at the transmitter. Then the other side of that is how many are received, and we're using the same laser array that we power the spacecraft propulsion system with, i.e. the laser array that's used to receive the photons. So that's a key part of the optical communication system. That has to be folded in. The other part is the noise is the combination of all elements in the system which produce noise. So in addition to just the sort of readout noise, if you want to think about it, although it's not quite readout noise, but there is a noise in the detection process. But there's also the primary sources of noise are the zodiacal light, which is the emission and scattering of dust in the solar system. So there's plots in our papers. If you go on our website and look at the Roadmap to Interstellar Flight paper and the other JVIS paper, which is about to come out, you'll see the calculations of the backgrounds from the zodiacal light and the cosmic infrared background. Those are the 2 dominant noise sources, and those set the fundamental limits to optical communications for interstellar space. The fact that you have a narrow laser beam that has a narrow line width is folded in. So all these are folded into that plot of the, let's see, it's on chart 16, which is the wafer scale one. I don't know if you can bring it up, Travis.
Yeah, it's up.
Okay, so on the right side, the one that's marked photon rate at Earth in photons per second, the dashed red line, that's the photon rate at the Earth, assuming a burst mode 1 watt, which is very modest on the wafer, and it assumes that you use the array that you transmit with, again, to receive, and folds in the backgrounds as well. And so if you follow, it's hard to see on that plot, it's highly compressed, I apologize, but you'll see that it's about 8 kilobits per second is the burst rate during a burst cycle.
Okay. Question for Travis. So thinking about this technology, which is very small in mass and doesn't decelerate at the target star system, how do you sort of envision that scaling into the future where we can decelerate and we can eventually even send people one day to the stars? How do you see that trajectory going forward?
As in the trajectory of
how do you move from this architecture, which is high velocity, doesn't decelerate, very small mass, to move into a situation in the future, even if it's centuries, where you can send, decelerate and put things into the atmospheres of planets and even one day send people?
Well, I mean, what I see for that is using this to go map the interstellar medium and to go observe what we want to. Say we see something Alpha Centauri that looks of interest to spark that kind of mission. That would then lead to using that same D-Star 4 system, and we can accelerate something, like I said before, 100 kilogram craft to 1.5, much longer mission duration, but we could use the same laser technology to go to Alpha Centauri and maybe have humans on board.
So are you assuming then in the future you would have the mag cells and everything then plugged in because all the technology would have matured?
Yeah, we could, but like that's not what we're assuming for our
But
one
this
gram.
particular.
Yeah.
Can I just make a quick comment?
Yep.
This whole issue of deceleration, I completely agree with you that would be nice to have a mission that could go into orbit. But to be very honest, all the numbers we've run and all the people we've talked to who've looked at this technology, I'm not convinced that it works at all at the level it's needed. And one way to think about this is on the acceleration phase, 100 gigawatts is 660 newtons approximately of force. And you're accelerating over a length scale which is comparable to a significant part of the solar system depending on the size of the reflector. Which means in order to decelerate from relativistic speeds to orbital speeds, typically tens of kilometers per second to go into orbit around a mass, typical mass in the solar system, is really not. It's not practical with any system I have seen because you're going to have to decelerate with comparable to the acceleration force, which means you're going to have to decelerate at roughly a few hundred to 1,000 newtons on your system. And we've looked at mag sails, we've looked at E sails. None of them can really do that. And so that's.
We have a minute
Phil,
of silence.
yeah, I'm so sorry, Phil. I'm going to pause you for a minute.
Yeah, no problem.
We are observing the National 1 Minute Silence here today in the UK. So we'll be back with you in just a sec. Hold those thoughts.
Sorry about that.
Ladies and gentlemen, as I mentioned at the beginning, we are observing the National 1 Minute Silence in memory of the victims in Tunisia and their families, and to remind ourselves we have to continue to strive towards a better world and a better society. So the 1 minute silence starts now. Thank you, ladies and gents. Thanks, Phil.
Jill, can you explain? I'm sorry, I'm on the other side of the pond, and can you explain what the 1 minute was for?
There was a recent tragedy in Tunisia, and several British people lost their lives. So it was announced by the Prime Minister a few days ago that we would have a national 1 minute silence in remembrance.
Because of the situation in Tunisia recently.
Yeah, because several Britons lost their lives. So
yes,
we just want to mark the occasion today as a silence.
Of course,
thanks, Phil.
Yes.
You can carry on. Thanks, Travis.
Very important. No, it's very, very important.
So basically what the answer to your question is, if it is feasible, then yes, we would try to incorporate in one of our bigger scale systems. But as we look at it and talk to people, we don't see that as a possibility and a feasible option.
So, Travis, can you bring up slide 10, which is, shows reflector mass and speed versus mass?
Yeah.
Okay. So this is for a nominal either 1 or 0.1 micron sail with a density of 1.4, which is appropriate for a hydrocarbon-based sail. Glass is around 2.3 or so, so it's not very different. And the scaling is the inverse 1/4 power of the thickness, which is h, the density, which is rho, and the spacecraft mass, which is m0. And if you have a chance to go on our website, just pull up the 50-page paper and look at all the mathematics. You cannot do better than this with 100 or 70 gigawatt system without photon recycling. These are just fundamental limits of the physics of the system. So if you want to go to a 10-ton spacecraft mass, which is 10,000 kilograms approximately, the speed you're going to get at best is a little below 1% the speed of light, so 10 to the minus 2 for beta. And that's just fundamental physics. Now you could go from a 0.1 micron, which is the red line, which is 100 nanometers, down to maybe a 1 nanometer, putative graphene, single layer graphene sail in the future. And so you would then gain a factor of 100, going from 100 nanometers or 0.1 micron down to 1 nanometer. We're not assuming that. We're trying to, again, sort of stay on a roadmap that allows us to get to relativistic speeds with technology that we feel is credible now. I agree that in the future you will go to thinner sails, but if you look at the scaling, if you reduce the thickness h by a factor of 100 from 0.1 micron to 1 nanometer, you're going to gain in speed by 100 to the minus 1/4 power, which is roughly a factor of 3 in speed. And that's just the fundamental physics of the problem, which is important. I mean, factor 3 is fabulous. It's fantastic. But, it's not you would love to have a factor of, 10 or 100 in speed, but you're not going to get it unless we overthrow our understanding of physics.
Maybe the last question, if there's nobody else. You accelerate the spacecraft during a very short period, and the power density is probably very high, probably something like gigawatts per square meter.
It's around there, right? So.
Yeah. So again, I apologize for going back to a paper that you don't have in front of you. Travis can print that out for you if you want. You can, print out the paper and look at it. There's a plot in the paper that shows the absorption for various kinds of high-quality glasses. So Z-bland is a particular kind of glass used in fiber optics, which has absorption of around 10 to the minus 12 fractional absorption per micron thickness. So that more than meets our requirements. If we use a multi-layer dielectric with no metal, we can still get modest reflectivity, say 90% or 99% reflectivity, which is good enough for the physics of acceleration, and it will easily handle the gigawatts, more like 100 gigawatts per square meter. If you just take just an ordinary fiber optic, a single mode fiber, and pass a 1 watt signal through it, you're already in excess of 10 gigawatts per square meter with a lowly 1 watt in a 10 micron fiber single mode system. And so you can make reflector materials that have low enough absorption to withstand that, as long as they don't contain metals.
Okay. So have you calculated the temperature at the end of the acceleration phase of the material?
Yes. So we've run simulations of radiation balance. So we looked at the emissivity of the materials that we're using and how much they radiate versus how much they absorb. And our goal is to keep everything around room temperature. Room temperature, you radiate about 500 watts per square meter. That's approximately what we get. And so that was our goal, is to keep things relatively cool. If you go to a model which is very different, let's say you go to graphene sails. So graphene sails in general are absorptive sails. There may be a way to make them reflective, highly reflective, possibly. in the future. It's not clear yet, but at the moment, if you take graphene, you illuminate it, tends to be somewhat absorptive. So there, you're fighting a completely different battle. You're fighting a battle of when does the graphene fall apart at high temperatures. We're not trying to fight that battle. We're trying to keep the temperatures low enough by keeping the absorption incredibly low. And so if you have time later, and Travis can bring up the paper, he'll show you a plot of absorption fraction for various materials. And like I say, we're kind of in a different regime. We're not trying to get to the ultra high temperature regime that some people have looked at. We're keeping things at very low temperatures.
Okay. So maybe one quick.
Plenty of time, Andreas.
Okay, because I thought you're quite extreme in terms of velocity. I mean, you are like 25% of speed of light, or maybe more than that.
Yeah.
So my question would be, why haven't you? I mean, the infeasibility of deceleration. I agree with you. At these velocities, it's almost impossible to decelerate within reasonable time. But have you thought about going down with velocity and then thinking about different means of deceleration, etc.? Because you have 100 years, I mean, in terms of the requirements, mission requirements of the competition. So have you thought about exploiting these 100 years?
We have, yeah.
Travis, can you bring up slide 14?
Yes. Which one is that?
Payload options.
Oh, yeah. Yeah, so yeah, this outlines the various ones that get to Alpha Centauri in 100 years. So we have a 1 kilogram spacecraft that gets there in 93 years. But decelerating, all we looked at was a mag sail, and as we looked at it, we found that it doesn't look very feasible. In terms of the technology behind. It was actually looked at by a NIAC study 13 years ago, and since then there has not been much progress.
So there's been an enormous amount of work done by i4is Interstellar into the Project i4is looking at mag sails. I cite papers by Robert Freeland in particular, one of which is in James at the moment, one of which he published. He presented at the last Starship Congress in 2013 extensive calculations on mag sails, and he showed that they are feasible, but there were constraints. There was also a paper by Malcolm Minovich, he's a mathematician, who came up with gravity assist, who also looked at mag sails. So he made some assumptions which are questionable, but there's been a lot of updated work on mag sails post-Super and Dana Andrews, which might be worth going back to look at.
So, Calvin, I believe that's you speaking? Is that correct? Okay, hi. I think we know each other at least through email. Let's see, so I believe the issues with the studies that you quote, they make a number of assumptions about the superconducting materials that they're going to use and the lengths of materials. And when we looked at that and talked to people at least have looked at these, it's not obvious at all to me that one can do that in a modest mass craft, even ignoring the fundamental facts of doing superconducting multi-kilometer hundreds of kilometer class loops. I don't I wish it were otherwise. I really wish we could come to you and say we have a design that works on paper for a 1 kilogram class craft, which gets you to the star, gets you to Alpha Centauri in less than 100 years, and it can decelerate using reasonable technology. I don't believe that is. Those are commensurate statements.
So there's a good point. I mean, the updated work was all looking at very large systems, like as in mega to gigaton systems. So
yes, and
so
that doesn't get you the
scalability issue when you go downwards. Yeah.
Well, I mean, keep in mind, at the kind of speeds that we're talking about, even if we go to the lowly speed of 4% the speed of light, which would get you there just barely in 100 years, 4% the speed of light. And you can compute the kinetic energy of, say, a 1 kilogram class craft, there's another plot in the paper that is on our website that shows the kinetic energy as a function of speed and mass, and you'll see that you're in the, you're getting up into the sort of many kilotons to megaton equivalent per kilogram of mass. And when you work that backwards and ask what does it take to decelerate that craft with the kind of technologies that we've just been talking about, and e-sail, mag-sail, interstellar wind, radiation, I have not been able to find a single one that passes my credibility test. I wish it were otherwise, and maybe out of what you guys talk about today will come that solution. But I scratch my head on that. I just don't see it.
Any more questions?
Well, last one. What will be the next step for you? Where will you build your phased array?
I think the next step for us is the laboratory measurements, actually, to kind of raise interest for this and maybe potentially do some sort of CubeSat mission. We'll see where it goes.
A question: did you look at solar pump with the lasers? Solar pump with the lasers?
Solar pump lasers?
Yes, we did. The solar pump lasers are nice in the sense that you directly pump the laser medium with photons from the sun rather than going through a conversion process of going sunlight to electricity to driving a laser. There are two issues with solar pump lasers that we kind of decided that was not the baseline direction we'd want to go. I mean, we keep a very open mind, so if there's a good direction that's scientifically valid, we will definitely look at it or try to incorporate it. Solar pump lasers can be relatively efficient. They're not as efficient as the current solid-state lasers, which are now very close to 50% efficient. But they do have the advantage that you don't have to go through a conversion process to electrical. But phase locking solar pump lasers is something which has not been done effectively before with low phase noise. And so I agree that at least in the idea world, it's nice, but I don't know how to accomplish it in reality at this point. So we did look at it. We decided it was not consistent with building a realistic laser of the kind that we could, say had a roadmap to a conclusion. Agreed, it's a question mark to be considered as we march along, but it's not on our baseline. Not because we weren't interested. We took a long look at it, but because it didn't do what we wanted it to do.
Okay, no more questions for Phil or Travis. Okay, thank you very much, Alex.